Right. All right. Let's go to. Okay. So here we are. This is what they came up with. Find the time. I think that's what we came up with. That's what we did. They made it all positive, which is, meh. Well. Notice what they did here. They made A. They just left it A as the negative. I bring the negative out and put it here. It doesn't matter. It doesn't matter. It's an plus a negative or minus is the same thing. All right, algebraically. So, what are the final velocity of the carrier package? All right, so we did that. Found its final velocity, negative 143. Okay, now here's a cool conceptual problem. Suppose you're driving in a convertible with the top down. The car is moving to the right at a constant velocity. You point a rifle straight up in the air and fire it. In the absence of air resistance, where would the bullet land behind you, ahead of you, or in the barrel of the rifle? Okay? And the question and the answer, drum roll please. Wait, I was looking for something over here real quick that's kind of cool, but I don't see it. Anyway, it's kind of a neat conceptual answer. It's going to land in the same spot, and there's all kinds of little videos where they show, at MIT and stuff like that, where they shoot a little cannon in the air. They have a little cannon on a cart. They shoot it in the air, and it comes along. Why? Because the x component of, if we neglect air resistance, if the x component of this is true, it stays the same, then it's going to ride and it's going to come down here. In the real world, here's what happens, especially if you shoot a rifle. Okay, that's why I used to be a little bit nervous. Actually on Stowers, at the Stowers building, on New Year's Eve, and mainly on New Year's Eve, on the 2nd of January and stuff, their janitorial crew goes on the roof of Stowers and they pick up all kinds of bullets from people in the surrounding neighborhoods around here, firing pistols in the air and stuff. That's kind of scary, because you think, oh, well, if it leaves the barrel at 250 meters per second, then it's going to come down at 200. No, it doesn't. It goes up in the air, it tumbles around, and when it comes back down, it reaches a terminal velocity of about half that. So it could still hurt. I mean, and it could even kill you if it hits you just right, but for the most part, it does. But for our purposes, shot it, boom, should come right back down. But that's really not what happens with a bullet. But you can see these little cart videos and stuff where they do that. All right, now let's talk about this problem. Let's talk about this projectile motion problem. Now here, see the first one is you might have seen on the Word document that has the videos on it. I said it's a half thing. All right, so now we're going to determine the range and the maximum height of this ball. All right, he kicks it 22 meters per second at 40 degrees. That's all the information I need, because there's a lot of implied information. And the implied information is what? Gravity. The acceleration in the y direction is equal to negative 9.8 meters per second squared. So let's just do this problem. I'm going to find the time until I get the time, I can't do a darn thing. Without time, I'm lost. Okay? Without time, I can't do anything. Okay? So, because that's what physics is. It's studying the time rate of change of things happening in nature. So we need the time. All right? And I probably spent too much time on that. Anyway, here we go. So a soccer ball is kicked at 22 meters per second. It's pretty darn quick. All right. And this, again, schoolhouse problem. 40 degrees, initial velocity. So it's got a v naught x, it's got a v naught y, and the acceleration we know is this. All right. So here's my soccer ball. It's been kicked this way at 40-degree angle. I want to find its maximum. Now we could do problems where we could say, oh, find its height, find if the they're about 3 meters high. A crossbar is 3 meters high. Would he make it? And that would be in those types of problems. That would be he kicked the ball. Here's the crossbar. It's this high. He kicked it like this. Did he clear the crossbar? And that kind of stuff. So you'd have to find the time when it's at this particular height. The time when it's at this particular height. Okay? And you find the time, find that particular, so whatever. And if your parabola looks like this, of course he's not going to make it. If it looks like this, he made it. Those get kind of tricky. I just want us to do the basics. And you're going to have a question on the exam, and it will just be the basics. It'll be like what we just did with the airplane, or it'll be one of these where it goes both, goes the full trip. All right? So we've got our x-coordinate stuff. And we have our y-coordinate stuff. And we just write down what we know. What's the first thing I know? I know that v naught x is equal to v, because here's 22 meters per second going right here. Let me redraw that so it's a little bit neater. Look what's going on right here. Here it is. This is 40 degrees. This is v is 22 meters per second. I'm going to break it down into its two components. It's got a v naught x and it's got a v naught y. Those are the two. That's the important thing right here. This is a 90-degree angle. All right. I just slid that v naught y over there. V is equal to cosine times 40. All right. For projectile motion problems, the cosine will be on the x-coordinate. When we get to forces later on in chapter 4, after the exam, you'll see that it's a little bit different. I mean, you'll have to know, oh, it's the adjacent leg that we're messing with. All right, v naught y is equal to v times the sine, the opposite leg over the hypotenuse, times the sine of 40. So v naught x for this problem is equal to 22 times cosine 40. Some of you with the older calculators will have to go 40 cosine times 22. That's 16.9. Let's call it 16.9 meters. Let's use 3 sig figs per second. V naught y is equal to 40 times the sine. 22 times the sine of 40. That equals 14.1. Let's go with 14.2. It was 14.14, so let's bump it up there a little bit. All right, so that's 14.2 meters per second is v naught y. Acceleration x direction 0. So my range, I know the range, how far this ball is going to go, is equal to, neglecting air resistance, I think I've kind of beat that to death, v naught x times the total time the ball's in the air. Okay? Times the total time the ball's in the air. V naught, the height, the time total, I don't know. The height that it goes, I don't know. Okay? And the height that it's going to go, or y max, let's call it y max, which is the height. Let's call y max the height that it's going to go, is going to equal, now think about this. The only thing I know is the acceleration is equal to negative 9.8 meters per second squared. What is the velocity in the y direction at the max height? What is that velocity going to be? 0. You're absolutely right. In the x direction, in the y direction. In the x direction, it's still going to be 16.9 meters per second. In other words, when it gets to its maximum height, here's y max. Here's y max. When it's here, v naught or vy is going to equal 0. V naught vx is going to equal v naught x. All right. So I know the time that it took to get to the max height. I've got 2 times I can mess with, and that's T max. T max, Mother Nature loves symmetry, is equal to time total divided by 2. Okay. Well, that makes sense. All right, and then so T max, but look, V naught Y max is equal to V naught Y minus 9.8 times T max. Oh my goodness. 0 equals 14.2 minus 9.8 T. 9.8 T equals 14.2. T is equal to 14.2 divided by 9.8. That equals 1.45 seconds. T max. So T total times 2 would be 2.9 seconds. So I've already calculated, so I've got everything I need. And if you want to, now remember, it's got to be for this kind of problem. It's got to be for this kind of problem where we start here and we end here. Then you know this, that the time to the maximum height is equal to the initial velocity in the y direction divided by g. Okay? The absolute value of g, or 9.8. Okay? There you go. And the total time of the flight is equal to, total time of the flight is equal to 2 times T max. All right? So we're about done with this one. Let's review the bidding. This might be a little bit long of a video, but that's okay. Let's review the bidding real quick. The key was, I'll review it a little bit later. So the range that it went was V naught X times T total. And V naught X we calculated was 16.9 meters per second times 2.9 seconds. .49 meters. Okay, and then the Y max, which is the height, maximum height, Y max is equal to V naught Y times T max minus 1/2 9.8 times T max squared. Okay? Or, I mean, that'll work. Let me show you this. So V naught max was what, 14.2? Yeah. So you got 14.2 times 1.45 minus 4.9 times 1.45 squared, which gives me 10.3 meters. Okay? Now, the other way we could do this is you go, well, wait a minute. Y max is equal to the average velocity, since it's a constant acceleration, the average velocity of the thing, in the y direction times T max. I know T max is 1.45. The average velocity would be 14.2 2 plus 0 divided by 2. So this equals 7.1 times 1.45, and guess what that equals? 10.3. You can do it that way too. It's all very flexible. And then I'll show you, we'll kind of go off a little bit, but we'll be fine, and then we'll wrap